Okay, good morning everyone. So before I get started, let me say that I've enjoyed questions and discussions with quite a lot of people. I'm leaving at the weekend on Saturday afternoon, so if any of you have things that you've been meaning to talk to me about but haven't got round to it, the next couple of days are the opportunity. Okay, so in my last lecture on Tuesday, in the second half, I talked about the Lieb-Shultz-Mattis theorem. And what that tells us is that if we have a quantum spin system that it applies to, which has neither ground state degeneracy because of conventional order parameter and broken symmetry, nor a branch of gapless excitations, then it must have the kind of ground state degeneracy that we now recognize as coming from topological order. And what I want to talk about in this lecture, and to some extent in the final lecture, is quantum dimer models, which are models at least somewhat related to spin problems, which exemplify this kind of topological order in quantum systems. And the general idea is to take classical dimer models and give them some quantum dynamics. And of course I spent the first half of the lecture on Tuesday talking in quite a lot of detail about classical dimer models so as to build up that background. I think it turns out that quantum dimers give us such a useful set of problems that there's a lot to be said for diving in and thinking about them just in their own terms, starting from the definition of the model, which I'll give you soon. But probably it would be unreasonable to start there without any kind of introduction at all. So let me begin by saying a little bit to try to give you some motivation. So this goes back a long way to something called the RVB picture, resonant valence bond picture, due to Anderson in 1973. And the problem he was thinking about was what's a good way of describing the ground state wave function for a quantum spin liquid. And so the contrast is with the situation in a spin system that shows Néel order, where of course we have a zeroth order model for the ground state wave function, just thinking of the classical state represented by a product wave function. So the basic idea was that to describe the ground state wave function for a quantum spin liquid, we think in terms of a basis of short-range singlets. So in some pictorial form, the wave function has components which we can think of as different arrangements of singlets on the lattice. So if I sketch in a bit of the lattice, one of the basis states would be some particular arrangement of singlets, and another basis state would be a different arrangement, and so on. So once you start thinking in these lines, you come to a great many questions, and I'm just going to mention a few and then avoid addressing any of them. So, I mean, one point is that these different states in the basis that we're thinking of are definitely not orthogonal to each other. And another question you should certainly worry about is whether a basis like this has a chance of being complete. Certainly it's not complete for all the states in the Hilbert space of the spin system, because by construction these are all singlets, but perhaps it's complete in the space of total singlets. Once you start trying to think of a spin liquid in this sort of basis, then for symmetry you'd like to ask yourself what the Néel state would look like if you tried to write it in this kind of singlet basis. And certainly all those questions and more have been thought about in lots of detail, but I'll just leave them there and go on to define quantum diamond models. Any questions at that point? So the idea is to take the set of diamond coverings that we were looking at for classical diamond models and simply take those as the basis states in Hilbert space and just assume by definition, which wouldn't be true if these states came from spin singlets, the different states are orthonormal. And one beautiful thing about that is that it builds in the ideas of different topological sectors that I talked about in the last lecture, and it also gives us the possibility, according to whether we think about diamond coverings on a bipartite lattice or a non-bipartite lattice, of having a Hilbert space with these built-in properties being either equivalent to a U1 theory or a Z2 theory. So what we need to do is to write down a Hamiltonian that will give us some quantum dynamics, and typically Hamiltonians have potential terms and kinetic terms. So here the potential term should be diagonal in the basis that we're thinking of, and the kinetic term should get us between different states in the basis, and it's reasonable to take them to be as local as possible. And the suggestion for the square lattice by Roxar and Kivelson looks schematically, and I'll write it down in the conventional way and then explain the meaning in a bit more detail. It looks schematically like this. So this kind of notation is absolutely standard, but it maybe needs unpacking if you're seeing it for the first time. So the idea is that this is a sum over different plaquettes in the system, and these bras and kets should have a plaquette label, but somehow we never write it in, and this refers to a part of dimer configuration on the particular plaquette that this is looking at, in which the dimers are in this configuration. So the action of the term in the sum that refers to this particular plaquette, when we look at this bit of the Hamiltonian, is to take a state like this and replace it with one where the dimers are in the vertical direction, and it does it whatever is going on in the rest of the dimer configuration. Of course, these two arrangements of dimers on a specific plaquette are not the only things that could happen in a configuration. So it could be that I have something like that, in fact anything other than this pair of dimers, and this term in the Hamiltonian acting on this plaquette will annihilate all of these other configurations. And then in a similar way, the potential terms, well, if this potential term acts here, because it refers to a vertical pair of dimers, it'll annihilate this, but this potential term will just weight that configuration with a weight V. And it's natural to think of the hopping term, the kinetic term, as having negative coefficients. So I'll take this parameter t to be bigger than 0, but I'll consider both signs for the potential term, which is this one. So if we're thinking about the model at 0 temperature, then we have one dimensionless parameter, which is the ratio of V over T.
Question?
Yes?
So there you raised all the issues about the non-orthogonal completeness, but here you did diagonal completeness, but here you say it's an orthonormal basis if it's classical diagrams, but then it looks a little bit similar. So why is this one orthonormal?
Well, it's orthonormal because we say it's going to be. So it depends. Originally in the lead-in to the motivation, the idea was that you took a spin model and then you could construct spin singlets across, for instance, nearest neighbor bonds, and that gives you a wave function which is written in terms of spins. But here we're just taking the kind of general spiritual motivation from that, but now we're simply saying that our basis states have no longer got anything to do with spins. They are these dimer configurations.
What is the advantage that we expect by going to this dimer model language?
Well, I think often in physics, I'm taking that as a kind of philosophical question. So, often in physics you really do gain by thinking of very simple models which abstract the essentials of a problem. And sometimes, people think of them and they're attractively simple, but they don't actually help you make much progress in a field. But on the other hand, there are models like the Ising model, or
So in the end, this model is going to be easier to treat than actually the simple spins.
Yeah, enormously. So I could fast forward a bit and say that, well, there are two great things about this model. One is that it has a solvable point in this one-dimensional parameter space of V over T called the Roxar-Kivelson point, which I'm about to describe, where we know the wave functions exactly. The other thing is that of course, computer simulations are very useful for understanding what's actually happening with models. But for these frustrated spin systems, there is a real difficulty because there's a so-called sign problem in quantum Monte Carlo, which is an obstruction to learning about ground state properties. And to some extent, DMRG on strips is now giving you a route around that. But in that context, a very useful fact about quantum diamond models is that you can do quantum Monte Carlo simulations on them without running into this sign problem. And that's meant that we've been able to find reliable results for the phase diagrams when the equivalent calculations have not been possible for spin systems. Yeah.
If I understand correctly, this thing inside the system has some 2x2 packets.
Yes.
And do the system run all possible packets, for example, with sharing identical position?
Yes, yeah, they do. So, for example, the sum would also, take in these plaquettes and these plaquettes and so on, so that you tile the lattice.
If I want to write this model in terms of spin operators, do I get something local?
Well, you do run into some problems because if you try and push this back to a formulation in terms of spins, then you have to face up to this issue of non-orthogonality. So you're pushed to a different class of problems, really. It's not that you can simply expect to rewrite this Hamiltonian in terms of spin operators. Okay, and then a minor remark which connects with that question about plaquettes is that I've written things relatively explicitly for a square lattice, but you can also generalize easily to other lattices. And you do really want to find squares or parallelograms. Well, what you need to do when you're generalizing to another lattice is to find some convenient ring that you can let this resonance move or kinetic energy act on. So for the triangular lattice, then you have, for instance, a resonance like that, but you also have resonances like this, and so you have overlapping shapes. I mean, this bond, for instance, would be the same as that bond, and then there's a third possibility which I won't bother to draw. And for the honeycomb lattice, the natural thing to do is to take resonances around hexagons. So the kinetic energy term takes you between two configurations like that. Okay, and then that's the Hamiltonian. It acts on this Hilbert space of dimer coverings. So, in general, any wave function is going to be a sum over dimer coverings and I can write a particular dimer covering with some label C, and a wave function in general will be a superposition of states like that. And these amplitudes are what we need to determine if we're trying to find, say, the ground state of the Hamiltonian or some excited states. Okay, one more point about motivation. So one route to thinking about quantum dimers is this one from the resonating valence bond idea. But that's not the only one, and it's maybe the fact that there's more than one route that leads you to quantum dimer models that makes them useful. And another route is if you think about frustrated classical Ising problems and then add in some quantum mechanics in a way that allows you to think of it as a weak perturbation. So, to be specific, let's think about spin ice, and in particular the sort of Hamiltonians that Bruce Golan was describing as coming out of his neutron scattering experiments, looking at excitations in a field that was strong enough to polarize the spins. In those Hamiltonians, I think the terms that cause spin flips were weaker than the basic Ising terms, which would give you a classical set of ground states corresponding to the spin ice states with the Pauling degeneracy that I described. So if we turn on some weak quantum mechanics, then we expect to split that manifold of classical ground states, and if the quantum mechanical terms really are weak, then we can think of them as giving tunneling between different different states from the classical ground state manifold. So, for example, they induce spin flips around short loops on the lattice. And I mentioned to you that we can think of the spin ice ground states in terms of dimer coverings, admittedly with two dimers touching each point in the lattice. And so these quantum mechanical terms will generate precisely this sort of kinetic energy contribution when we go over to a quantum problem. Okay, so now on to one of the features that makes these models very useful, which was realized in the first paper by Roxar and Kivelson, and that is that there's a point in parameter space, the RK point, where we know the wave functions exactly, and that's the point where these two parameters are equal to each other. And at that point, we can rewrite the Hamiltonian. We have a single parameter which we can take out the front, and still this schematic sum over configurations. But then for each plaquette, we can think of just having a difference between two terms. Because if we expand the brackets, then we generate the potential term with a positive coefficient and the kinetic term with a negative coefficient. Now, each term in this sum is a projector, and this coefficient is positive. So the Hamiltonian is a sum of projectors with positive coefficients. So if we can find a state with eigenvalue 0, then that must be a ground state, because the eigenvalues of this Hamiltonian are non-negative. So the point is that for a single plaquette, we could think of, well, we have states like that, and then various other states where we don't have a pair of parallel dimers on the plaquette. So we can take symmetric and antisymmetric combinations of these two, and this projector is just onto the antisymmetric combination, obviously, and these states anyway are orthogonal to these other ones. So the nice thing is that the ground state has all of these amplitudes the same, at least within a given sector. And the sector should be a set of states that are connected by the kinetic energy term in this Hamiltonian. So actually that leads us to the question, what is the set of states that's connected by these local dimer flips? And the answer depends a bit on the lattice, and in some cases you need to add some slightly longer range dimer flips to get a set of connected states with some sensible properties. But what you might anticipate, and what turns out to be more or less the case, is that the set of states that are connected by these local dimer moves are just the states within a given topological sector of the classical model, in the sense that I described it in the previous lecture. So why is it obvious that a state like this with equal amplitude for all of the configurations in a given sector will be the ground state? Well, the point is that if we focus on a particular plaquette in the system, then in the different configurations, various things can happen on this plaquette. So one thing that could happen is that we have some dimers in some configuration that's not one of these two pairs of parallel dimers. That will be annihilated by all the terms in this Hamiltonian anyway, so that will give us a zero contribution. Or otherwise, we could have either configurations in which that happens on the plaquette we're focusing on, or configurations in which this happens. And in an equal weight superposition, for each arrangement of the dimers away from the plaquette that we're focusing on, we'll have this and this with equal weights, which means that the contribution to the wave function is some state for the rest of the lattice, tensor multiplied by a combination like this, but with a plus sign in. And so this projector, again, annihilates that state. So this is a state with zero energy. So I hope that's clear, but if any part of the argument is not, then say now, please.
Yes, so I take basically the sum of these two with equal weight. So can you show again why
Okay, so the point is that we have a term in the wave function which, if I write it more explicitly, for this particular plaquette has that plus that. And then if we're being a bit more explicit about how we write our wave functions, this is multiplied by something for the rest of the lattice. Now, if I take the overlap of this with that, then my claim is just that sorry. It's that this overlap gives me zero, because this gives me plus 1 and this gives me minus 1. So it's okay. Yeah.
What do states on different sectors looks like?
So then we need to think of our system on a torus, and we look at the flux winding around the torus. So if it's a non-bipartite lattice, I just look at the parity of the number of dimers crossing a line, and otherwise I orient the bonds taking account of the bipartite structure. Okay, so at least at this special point in the zero temperature phase diagram, we have a nice simple state, and we can think about its properties. And the great thing turns out to be that we can lift some of the stuff from classical dimer models to say things about this quantum wave function. So if we think about correlations, then for an observable that's diagonal in this dimer representation, we can work out ground state expectations, they're just averages over the classical configurations. Because what we'd want to work out, if we have some operator, is and if this is diagonal, but if these A's are all 1, then this is just a sum over classical configurations of some of the observable that we're interested in. So what that means in particular is that if we look at dimer-dimer correlators, then if we're on a bipartite lattice, they have the Coulomb phase correlations, these power law correlations that I was talking about in 2D and 3D. And on a non-bipartite lattice, they have exponentially decaying correlations. Which again is something we know from the classical dimer problem. Right, sure, and I'm going to come on and talk about excitations, but not for a little bit yet.
But it's gapless, right? That's the point.
It is gapless, yes, yes.
So is the kinetic term enough to reach all possible configurations of dimers? Always, in any lattice?
Well, the most that you could hope for would be that it would reach all configurations within a given topological sector, because the idea of these sectors is that they're the states that you reach by local rearrangements. The details depend on the particular lattice, but it may happen that you have some dimer configurations within a given sector which you can't escape from by making just moves around the smallest loops. But at least in the examples I know of, it turns out that when you add flips around slightly longer loops, then those states are connected to the other states in the sector. So it doesn't seem to be a problem to get ergodicity within a sector from kinetic terms of this kind. So apart from asking about dimer correlations, you could also think about what happens when you introduce monomers. And at the simplest level, these could just be static monomers, so that the Hamiltonian doesn't give the monomers any dynamics, but you still allow the rest of the dimers in the background to flip in the same way. And then at the Roxar-Kivelson point, you still have exact zero-energy eigenfunctions by taking equal amplitude superpositions of all dimer configurations that are compatible with particular positions for the monomers. So you still have ground states with zero energy. And that's zero energy regardless of the separation between a pair of monomers if you think of introducing this pair by breaking up a dimer. So that's saying that you have exact deconfinement or perfect there's no interaction at all between the monomers.
How do you introduce such monomers? Because we understood that we create Hilbert space by just considering a basis of dimers.
Yeah, okay, so you have to extend the idea of the Hilbert space and say that with a certain number of monomers, an even number of monomers, the configurations that you allow have each lattice point either covered by a single monomer or touched by a single dimer.
Excuse me, do we have something similar to pulse instability in this system? If there is, then why there's monomers in ground state sector?
Well, whether or not there are monomers there is really according to which Hilbert space sector you choose to look at. I mean, I think you want to consider separate sectors with either no monomers, one pair of monomers, two pairs of monomers, and there's nothing in the Hamiltonian that would connect them. So you'd have to generalize the model quite a bit to come to a question about instability. But, I mean, it could have happened that, and if we go away from the Roxar-Kivelson point, then it may happen, as I'll discuss, that the dynamics of the dimers would result in confinement of a monomer pair so that they were close to each other. But at least at the Roxar-Kivelson point, that's not what happens. You just have deconfinement.
Just to make this clear, so we consider dimer configurations where each lattice point has one.
Yes.
Is connected.
Okay, and that's all I'm talking about. But you can imagine extensions which would be relevant, for instance, to spin ice, where you have exactly two dimers covering each lattice point, and you could run similar arguments.
Well, I was thinking of less dimers.
Yeah, no, you might ask what happens if you have a lower density, so it's not completely close packed. But actually, I don't want to talk about that. Well, that would correspond to some density of monomers. So I guess I have talked about it. Okay, so this is what happens with monomers at zero temperature, where you're just taking averages over this ground state wave function at the Roxard-Kivelson point. You can also easily enough discuss what happens at infinite temperature, because at infinite temperature you don't care about this Hamiltonian, and you just go back to the classical dimer problem in the presence of possibly some static monomers. Yes?
Sorry, I still don't understand how this Hamiltonian will act on monomers.
Yeah, okay, it's true that I would really need to generalize it to include what happens with monomers. And what I'm saying at the moment is that we have some extra states for a plaquette, which might, for instance, one of them would be like this, with a dimer there, and the point I'm emphasizing is the presence of the monomer here. And I simply want to say that a state like this with a monomer on the plaquette is orthogonal to all of these. And I mean, I could also introduce some dynamics for the monomers, and you can actually do that, and Roxar and Kivelson do, and you can write down a wave function given the monomers dynamics, but I won't talk about that. So we can compare with infinite temperature, where we had the results from the previous lecture. So then whether monomers were confined or not depended on whether we were on a bipartite lattice or a non-bipartite one, and whether we were in 2 dimensions or 3 dimensions. So for a 2D bipartite case, you remember via the height model we had a logarithmic growth in energy as a function of the separation of a pair of monomers. So we had log confinement. And on 3D bipartite, that corresponded to monopoles in spin ice, and as I discussed, we have their deconfinement. And also 2D and 3D non-bipartite. We have deconfined monomers. So, I mean, the fact that we have deconfinement at the RK point at zero temperature is not trivial. These infinite temperature results obviously apply for all values of T over V, since the Hamiltonian then is irrelevant. Okay, so the next thing that I want to talk about is the phase diagrams for these dimer models as we vary the ratio of T over V. And first of all, I want to talk about some extreme cases, and then I'll talk about how the phase diagrams actually look, and the results depend on, again, whether we're in 2D or 3D, and whether we're looking at bipartite or non-bipartite lattice. So let's think first of all what happens if we make the potential term, make the coefficient of the potential term bigger than the coefficient of the kinetic term. So then the Hamiltonian is the one that we had at the RK point, plus V minus T times this potential term. So this is positive. So if we can write a zero energy state, then it must be a ground state, because this bit of the Hamiltonian is non-negative and this one is positive. So to write a zero energy state, we need to find a state that's not affected at all by this potential term. And in order for that to happen, there shouldn't be any plaquettes with parallel dimers on them. And that's the case in a staggered state. So on a square lattice, although you can do similar things on other lattices, what you want to arrange is something like that. Yeah.
Is there an even odd effect depending on the size of the system? You can imagine you wouldn't be able to do that kind of timing for an odd number of sites in one direction.
Yes. Yeah, there must be. So maybe you can't, if you make the system odd in both directions, maybe you can't write a nice zero energy state like that anymore. And then probably you have to have some domain wall which costs energy, and you have some freedom about where you put it. Another limit that's easy to talk about is what happens when V goes to minus infinity. And then what you want to do is maximize the number of flippable plaquettes. Which you can do by arranging a state like this, where you have lines of parallel dimers. And obviously, both this state at V goes to minus infinity and this state when V is bigger than T are broken symmetry states with several equivalent possibilities related by spatial symmetries. And in between you can imagine other possibilities, for instance, for instance, you could break symmetry in a way that schematically I'll draw like this. and this is something that's found in simulations and called a plaquette state. And what I mean is that the dimers resonate around this plaquette roughly independently of the dimers around this plaquette, but the probability to have dimers on these bonds, say, is lower. And
But you propose for equal into minus infinity, isn't an angle state of what I mean is that it's just that it's only for V equal to minus infinity as long as soon as V is really big but not equal to minus infinity.
well, okay, so the potential term will take maximum possible advantage of this because it's got as many parallel dimers as you can have. So that's why it's good as V goes to minus infinity. And then the kinetic term will induce admixtures of states like that, which is the point that you're making. Yeah. Yeah.
In the staggered state, I get the impression that domain walls have no energy cost in the limit where V is infinity. My question is that if it's the case, is there a simple reason to understand why they become costly when you introduce the kinetic energy term, virtual fluctuations? It seems that there's no flippable plaquette in any case. So in this case,
Right, so the staggered state, the claim is that it's the exact ground state for V bigger than T, so over the whole range from...
there are plenty of such states. You can put the
Yes.
walls between staggered horizontally and vertically. And my question is that don't you get, in this case, a larger ground state entropy because if these domain walls have no energy cost?
Yeah, although we're really thinking about zero temperature states, so we don't care so much about the entropy, but the question would be whether the kinetic energy term in the Hamiltonian connects these different ground states with domain walls in them. Yeah, okay. So the point would be then that there's a number of different disconnected ground states in this region V bigger than T. Okay, so that was discussing some simple limits, and what we'd like to do now is fill in the phase diagram, and mostly the answer comes from numerics, but let me just give a brief kind of plausibility. So what we're interested in, we know what happens for V bigger than T all the way to V equals plus infinity. We know what happens when V goes to minus infinity. So what we would like to know about is near the Roxar-Kivelson point for V just a bit less than T. And although it's certainly not definitive, you can get a kind of hint from looking at this T equals infinity behavior and asking yourself what might happen as you lower temperature from infinity to 0. On a 2D bipartite lattice, we have confinement at infinite temperature, and at the Roxar-Kivelson point, we have deconfinement, but somehow that's maybe a special case, and it's perhaps plausible, and it's what comes from simulations, that if we're not at the Roxar-Kivelson point, then this confinement that we get at infinite temperature continues down to 0 temperature. And so, in fact, you get, in the bipartite d equals 2 case, you get order for any v less than t. On the other hand, if we're in 3D, for either bipartite or non-bipartite, then we have deconfinement at infinite temperature, which is the same thing as happens at the Roxar-Kivelson point at 0 temperature. So it's perhaps plausible, and it comes out of simulations, that we have deconfined phase over a finite region of V over T. So the phase diagrams to give you results from quantum Monte Carlo. If we have a square lattice, then we have the Roxar-Kivelson point, and staggered phase everywhere to the right of it, and far to the left we have a columnar phase, and it turns out that just to the left of the Roxar-Kivelson point we have that plaquette phase. Whereas if we stay in 2D but go to a non-bipartite lattice, then again we have a staggered phase to the right of the Roxar-Kivelson point, but now we have a window with RVB phase. That's to say monomers remain deconfined, and we don't have any long-range order in the dimers, and we don't have any broken spatial symmetries. And so this is an example of a Z2 spin liquid. And then if we go far to the left, we get a columnar phase. And well, it's that state that I was drawing for V goes to minus infinity with rows of parallel dimers.
Where are the phase boundaries between the columnar and the plaquette? With those double lines?
Right, well, typically you get some... I think you may have some intervening phase in between, and I didn't want to get into the details of that. So, for example, you can look up more details in the article that I put on the school website by Mertner and Rahman. And then the third case to talk about is to have an example of a 3D bipartite lattice is the diamond. Where, consistent with this kind of phenomenology coming down from high temperature, we have a deconfined phase, but now because we're on a bipartite lattice, it's U1 RVB phase over some finite extent to the left of the Roxar-Kivelson point. Well, it's diamond because of the connection to pyrochlore, if you like. And I think you get the same answer. I checked through the literature to see which models had convincing simulation results for these three, and I forget whether the results are there for the cubic lattice or not. So looking at those phase diagrams, you realize that you want to interpret the fact that monomers are deconfined at the RK point differently in the case of the square lattice from the way you interpret it in the case of the triangular lattice. So what you see in the case of the square lattice is that the RK point is a critical point where you go from one phase with broken spatial symmetry to another phase with a different broken symmetry, and the conclusion must be that the deconfinement which you calculate for the RK point is deconfinement that's a property of the critical point. Because in either of these phases, if I try to move the dimers apart, then you expect a linear confining potential in the way that I explained in a classical context in the last lecture, because you have a kind of string joining the two dimers which disrupts the ordered background. Whereas on the triangular lattice, the RK point is the end point of a phase, and it's reasonable to expect that you have deconfinement throughout that phase.
So is it fair to say that this RK point in 2D is the simplest example of a deconfined critical point as defined by central infinity? Or do you all listen?
Yeah, simplest, that's subjective, but it's, yeah.
This sort of infinitely fine too, I think.
Yes.
In that sense, it's unsatisfying compared to the example they have.
Do you know an example of U1 liquid in 2 dimensions? Because it seems that...
Right, and so there's a good reason why there aren't examples, and that's the next thing that I want to say, although I can just point out a connection, which I'm not going to have time to go into in any detail. But the connection is to do with general properties of gauge theories. So if you take the two gauge theories, they have confined and deconfined phases in both 2 plus 1D and 3+1 dimensions. And I guess that was originally shown by Franz Wegner, who will be lecturing, I think, in the last week of the school. But if we think about U1 lattice gauge theories, then then there's a distinction between what's called compact and non-compact gauge theories. It's according to whether the U1 is a compact angle. And here, because we're dealing with lattice problems, we're really thinking about compact theories. And then it's known that U1 theories are always confined in 2+1 dimensions, but they can have deconfined phases in 3+1 dimensions, and this is a result due to Polyakov. So that's consistent with this difference that we have between the square lattice and the triangular lattice in 2 dimensions. So the fact that we only have this ordered phase, except at the transition point, corresponds to the absence of deconfined phase in 2+1 dimensional compact U1 theories. But on the other hand, if we go to 3+1 dimensions, then we can have a deconfined phase. Okay, so the next things that I want to talk about excitations, either at the RK point or in this RVB phase. So one simple point to make is that in the RBB phase, if we create a pair of monomers and hop one of them around a circumference of a system on a torus, then that will get us between different sectors of the theory. So if we think of a line around the torus, and to identify the Z2 sector, we're asking about the parity of the number of dimers that line intersects, and in a particular configuration we have a dimer there. If we make 2 monomers and then flip one of them, and keep doing it until it comes right round the system, then we get to a state where, after we've hopped this monomer right around, we have 2 adjacent monomers, and then if we recombine them to make a dimer, you see that we've change the parity of the number of dimers cutting a line around the system, and so we've got between different sectors. Okay, moving on from that, if we want to think about excitations, then it's a matter of thinking about wave functions, which are models for the excited states. So at the RK point, we have this uniform superposition with equal amplitudes of all the states in the Hilbert space. If we want to make excited states, then of course the wave functions we're thinking about have to be orthogonal to the ground state, and so something that we need to do is introduce some minus signs into the superposition. And one possibility is to try to make a point-like excitation with a wave function that has some minus signs depending on dimer configurations. And these point-like excitations are known as bosons in a Z2 theory, and they're basically insertions of flux into the system. So we're thinking about a Z2 problem, so we take a non-bipartite lattice, for instance the triangular lattice, and if we want to write down a model wave function for a system with an excitation, say there, then we choose some string that goes from this excitation either to the edge of the system, or if we have a system on a torus, to some other distant partner excitation. And we take a variational ansatz for the wave function, which again is some superposition of states from the basis, but now we attach a phase factor of -1 to the power of the number of dimers crossing this line. So one thing to worry about, of course, is whether the particular path that you choose for this line matters, and I'll leave it as an exercise for you to show that if you take some other path, then you get a wave function which is the same up to an overall possible minus sign, which depends on the relationship between the two paths. So this is a point-like excitation, and because you've done something reasonably violent to the wave function in the vicinity of the place where it's centered, you expect it to cost a finite energy. So the other kind of wave function that you might try and write down for excitations is something that describes more of a long wavelength density wave. In fact, you can't quite have density waves because the density of dimers is absolutely rigid, but what you can have is a kind of polarization wave where you favor dimers in one orientation over ones in an orthogonal orientation, and those more or less give you photon-type excitations. I say more or less because at the RK point, their dispersion is rather different from what you'd expect for real photons with frequency proportional to wave vector. But if you go away from the RK point, then those do become photon excitations. And I'll talk about those in the lecture tomorrow. Any other questions? Yeah.
Why is the Wison point-like but not string-like?
Because the particular path that you choose for this string is irrelevant. It's fairly easy to show, and so the only thing that matters are the endpoints. So the string is just a construction for writing down the wave function, but the excitation really lives at its end.
So you say it's variational, but is it exact for the arcade points of the triangular lattice?
No. I don't think so, no.
For that lattice, do we have the exact spectrum?
From Monte Carlo simulations, you know the energy. I mean, one thing to say is that because the Hamiltonian has translational symmetry, then if it's true that there are point-like excitations of this kind, the exact eigenstates will be momentum eigenstates. So you'd better be asking about the dispersion relation as a function of the excitation wave vector. And so the claim is that that's a dispersion relation with a gap. And you can determine that from simulations, but I don't think there's any exact result, say, for the minimum of the dispersion relation.
Taking the parameter, the energy to be negative, changes things a lot?
Yes, I think it would change things a lot. But I'm not sure what does happen. I mean, so with this positive sign, you know that the ground state wave function is nodeless in the sense that you have an equal sign for all of the coefficients. Probably you lose that if you flip the sign of the kinetic energy. But
The Bison wave function is not orthogonal to the ground state.
I think it's probably not exactly orthogonal in a small system, but I think it becomes orthogonal in a large system. So the point is that if you think about contributions from configurations related by flipping dimers around a large loop that intersects this string, then you get cancelling contributions, and so if the ends are far apart, I think the ends of the string that define a pair of Visons are far apart, then I think you get a wave function that asymptotically will be orthogonal to the ground state. Okay, thank you.